Welcome. This is Wireless Future. I'm Eric Larsson, and I'm here as always with my colleague Emil Björnsson. Hello, Emil. How are you today?
I'm doing great.
That's good to know. Emil, is this episode? I think this is episode number 10. Can that be correct?
Yeah, it is episode number 10. So it's starting to be a good habit to talk to you like this.
That's amazing. Number 10. Well, welcome back. So today we're going to talk about terabits, terabit per second, and reaching the terabit per second goal. I was reading, Emil, your paper here, scoring the terabit per second goal, broadband connectivity in 6G. And I thought, we'd talk about a few aspects related to what you write in the paper. So a terabit is a lot, many zeros. So if we back up a step then to 5G, what is the peak rate in 5G?
So when it comes to 5G, it will depend a lot on what you actually get in the real deployment, because that could vary a lot. But if we just look at sort of what the specifications are for being a 5G technology, then ITU, the International Telecommunications Union, they say that the 5G technology should be able to, in millimeter wave bands, deliver 20 gigabits per second in the downlink and 10 gigabits per second in the uplink.
20 gigabit per second, even that is quite a lot, right? So what does really, you say minimum requirement, what does it really mean? Is that like for a device to be called 5G, that it has to deliver this peak rate under some circumstance, or?
I think the intention is that a technology that wants to brand itself as 5G should be capable of doing that. If you look back at sort of 4G, there were the discussions, is LTE a 4G technology or not, at least the first releases, because it didn't follow all of those minimum specifications. But it's still just a theoretical type of thing. Someone sets up a minimum requirement for the technology to satisfy, and then someone needs to build a technology that can do that, but then whether it's actually used in every base station or every handset can support it, probably not. So it's still sort of in the best case scenarios.
Yeah, it sounds like it really has to be a best case scenario, right? So, how is this achieved? 20 gigabit per second is still a lot.
Yes. So on the one hand, it's sort of they set up this goal, and then they don't say that you don't need to follow their advice on how to achieve it. But what they mention in the specifications there is that they think that you should support at least 1 gigahertz of spectrum in the millimeter wave bands. There's no network that has that right now, but anyway. And then you should have a peak spectral efficiency of 30 bits per second in hertz. So if you multiply those things together, you get 30 gigabit per second, and that is essentially then what you are dividing between the downlink and the uplink.
Right, so 30 bits per second on hertz, that's a lot. So how is that done?
That's a good question. There's essentially two different things you can do there. You could try to transmit multiple streams or layers at the same time, and then in each layer you could play around with how many bits you are squeezing in. So say that we are sending 8 spatial layers with different polarization, different directivity, and then each one of them is using a 64 QM modulation with some 5/6 channel code that gives you 5 bits per second in hertz. So then 5 times 8 will give you something in the ballpark of what we are looking for. Then this is still the ideal cases, so we might not achieve exactly that in realities, but it's sort of given an indication of how they think that you would achieve it.
Right, so it all relies on a combination of fairly high modulation order, which in turn requires high SNR, I suppose, or SINR, and spatial multiplexing with multiple, spatial streams.
Yes, and I think 5G is actually supporting, I was mentioning 64 QAM, they're supporting 256 QAM as well, with some channel code. So you could, per stream, push it up a little bit further than I was exemplifying as well. But it's... there's a multitude of ways to achieve those type of things. And I think in terms of specification, you also only need to make sure that there is one option where you can achieve what the requirements by the ITU are.
Right. So, do you know what sort of spatial processing and antenna arrays there are used to get all these layers in parallel?
So I think that is sort of what ITU is leaving to the one who is designing the network to suggest. But I would guess that, of course, you need a large number of active antennas at your base station so you can transmit multiple layers. But if you're going to deliver this to one location only, you also need the receiver there, which might be a user device to be able to receive multiple things there. And I think maybe a device with 4 antennas is more likely for the moment than 8 antennas. So
right, and perhaps, I mean, you need like fully digital beamforming to do this, right? And we heard was that in the last episode of the podcast where we had a guest talking about fully digital now becoming a reality for millimeter wave. So that's quite amazing. So a terabit per second, that's a lot. How many zeros? Let's see. Giga is 9, right? And tera is 12. So 12 zeros. So terabit is like, what's that? I mean, a movie with reasonable quality DVD used to be like 4 or 5 gigabyte, right? So that's like 40, 50 gigabits. So this is like many such movies per second. Why and when would we really need this?
So I think there are a couple of different ways of answering something like this. One might be that we are pushing towards this target just so we could, on the average, get the more decent rate that we need. But then looking at use cases, I think the first thing that could come to people's mind is that, we would like this fully immersive virtual or augmented reality type of thing where you can look around and get 3D views of the world. But when people are really computing how much data that would be needed per second, you can say, how much do your brain need in order to process things around it so it feels like it's reality? It's probably much less than a terabit per second. So even if it might be that you would like to do everything uncompressed so you get rid of the delays because of compression algorithms, it might not be the right use case.
Yeah, still it's a lot. I mean, even just I think that the hard drive on my PC is like a terabyte, right? So it's like 10 terabits. So emptying that hard drive over the air in 10 seconds, that sounds just amazing. But perhaps it is just these new emerging applications with extended and augmented reality that will require these enormously high peak rates.
I think there are some other use cases that might be more practically useful for the moment. So one is what they call a data chosk scenario. So suppose your device is sort of either you have told it to download something for you, or it has sort of been predicting that you will like to watch this and that videos, and then for a less than the second time you pass by a small link that is just very quickly transferring all of this information to you, and that's what they call a data chosk over just a few meters distance.
So are you suggesting, because at least I think, you and me in papers, and also I know for operators in discussions on 5G, there's been a lot of talking about uniform quality of service, like you have a steady stream of data that you can rely on that never gets interrupted. But here it sounds more like this is intermittent quality of service, where you get a flash of terabit per second over half a second or something, and then the link is dead for a while. Is that a way to think about this terabit per second scenario?
I think that in order to sort of deliver an experience of always being connected, always have a great service, there are a number of different aspects to that. One is to sort of build an architecture that would be better at giving us good guaranteed or minimum rates, and I think we will go back to that in later episodes as well. But another option is to build an application layer that is sort of pretending to be like that. It's sort of, I'm going to now click on this video, and someone already predicted to download it in 4K quality, so you it's already there.
That's a great point. So in fact, it's really the experience by the user that we want to be uniform. Okay, yeah, that might be something we should return to in a future episode. So how?
I think I have one more use case that might be might maybe be the killer one here, and that is just much more boring. To say that you have a base station, a small cell somewhere, and then you have a bigger base station somewhere, and in between these two, you will have to deliver a lot of data, so that it's sort of a backhaul link between them, and then that small base station would then spread out that data between many users. Or you can view it as like connecting your home or your office with a fixed wireless link, delivering 1 terabit per second, and then within that office you have 100 people who are sharing that link in the end.
Right, I see. So backhauling large amounts of data. Well, I don't quite think that's boring. I mean, it sounds like a vital component of the infrastructure. But anyways, so how could one reach this enormously high rate? What would it take to get a terabit per second?
So the basic formula for data rate here is to take the bandwidth in hertz and multiply it with the spectral efficiency in bits per second in hertz. And that tells us that we have these two components to play with, having more bandwidth and having higher spectral efficiency. And there it's also important to mention that sometimes maybe in computer science, bandwidth is synonymous with data rate. Well, it's actually not, but you have this proportionality there. They're sort of viewing the spectral efficiency as being given, and then you're changing the bandwidth is the same thing as changing data rate.
Oh yeah, that's a great point. I mean, data rate is bandwidth multiplied by spectral efficiency, right? So
yeah.
How about more antennas?
So that is something that I then factored into the spectral efficiencies. Okay. We can divide that up into two pieces as well. It's sort of having multiple antennas, which is improving our spectral efficiency by taking for each stream, we beamforming the signals, we get a stronger signal, and that allows us to use a larger modulation format, like going from 16 QAM to 64 or 256, and then having these multiple spatial layers sent through different beams, so you can take the number of layers, multiply with the modulation format that you get, and that brings us the total spectral efficiency.
Right, so increasing the bandwidth and increasing the spectral efficiency, and a main tool to increase the spectral efficiency is to use more and more antennas and more spatial streams.
Right.
So, I mean, start with the bandwidth. So where do we find all this bandwidth?
Yeah, so that is typically that the higher you go up in the frequency range, the easier it is to find a large amount of bandwidth. So if you say like, we needed in 5G 1 gigahertz of spectrum, of course you can never find that below 1 gigahertz, because then you will need to use everything that exists. Okay. And the higher you go up, if you go up to 28 or say 39 gigahertz, well, maybe you can find 1 gigahertz of spectrum there to utilize. And that also shows that people are considering going further up in the frequency domain, and there are some projects that have been looking into these type of things, and in the 90 to 200 gigahertz bands, you can find probably 50 gigahertz that could be suitable. And if you have 50 gigahertz, you will need sort of 20 bits per second hertz to deliver 1 terahertz, the terabits per second. And if you go even further, between 220 and 320 gigahertz, so that's sort of towards the end of what we call radio spectrum, you can find another 100 gigahertz that seems to be potentially useful for these applications. And then if you have instead 100 gigahertz, you only need 10 bits per second hertz to deliver 1 terabit per second.
Right, 100 gigahertz. So yeah, so those were lots of numbers here. Let's see.
Yeah.
So you're saying essentially that going to hundreds of gigahertz carrier frequency, then there'll be lots of spectrum available because the relative bandwidth is much smaller there. So what sort of spectrum is this? I mean, if we go to like several hundred gigahertz, will there be licensed spectrum or unlicensed? Do we know that? Or how to get your hands on that spectrum, so to speak?
Yeah, so I must say that I don't know all the details around this thing, but I would say that this is sort of something that might not be entirely harmonized around the world, but it's sort of spectrum that is either not utilized because it's not a good propagation condition there. There might be things like gases that are absorbing the signal so it doesn't propagate very far, or it is things that are typically used for scientific purposes. Might be used for radio astronomy, like satellite services, maybe you transmit between satellites, or meteorology kind of things. And if you are going to use this spectrum for now radio communications as well, then you probably need to find a way of coexisting with those existing things.
Right. On the other hand, I mean, I suppose the range will be quite short, right? So you
Yeah.
might not, cause a lot of harm if you transmit with small power in these bands.
Yeah,
But
as
on
long as you stay away from this super expensive, radio astronomy
oh
equipment
yeah,
that are at a few locations in the world.
oh yeah, don't get anywhere nearby there, I suppose.
Yeah.
Yeah, it'll be interesting to see. I mean, how business models will play out in these bands, and if any of the spectrum ends up being licensed, then what will the cost be? I'd expect to be dirt cheap, right? I mean, per hertz at least,
Mm.
compared to the lower frequency bands that
Yeah.
have been sold for like hundreds of US dollars per hertz in the last few years.
Yeah, and this ITU, the International Telecommunication Union, they are also having efforts in trying to harmonize the use of spectrum. So they sometimes they have the World Radio Congress where they are sort of talking about what spectrum do we think is going to be used in 5 to 10 years, and what can we do in order to harmonize the licenses. We can build one technology that works in most countries.
Yeah, right. I see. So let's talk a little bit about, I mean, we talked about bandwidth, right? So let's talk a little bit about spectral efficiency as well. And so I think you mentioned like, did you mention 20 bits per second on
Mm-hmm.
hertz earlier? So how could we achieve that? That's a lot, 20 bits per second on hertz.
So if we just sort of look at one stream of data, one layer, then you can push up that to some extent. So I think one of the latest Wi-Fi standards, the 802.11ax, that is sort of the distinguishing thing, they support what is called 1024 QAM modulation, which if it's uncoded, so everything is useful data, then you get 10 bits per second hertz just by using that modulation. Then you usually have coding on top of that. The problem with something like that is that you need a high signal to noise ratio to be able to decode it. So say 35 decibel of signal to noise ratio.
Right, so 35 dB signal to noise ratio gives you about 10 bits per second in hertz, right? I mean, that's the Shannon formula, log 2 of 1 plus the signal to noise. That's a lot. That's
Yeah.
not, I mean, I'd suppose that with 10 bits per second in hertz, you'd be at 1024 QAM modulation. You'll be extremely sensitive to phase noise for one thing. And also, it's getting 35 dB signal to noise is not an easy thing. I mean, for one thing, you'll have to be, I suppose, rather close to your transmitter. And also, there must be no interference whatsoever. Is that really, I mean, is that realistic? Does this work in practice?
I think this is also sort of chasing the peak rates to show that its technology is able to do something in the best cases. But I mean, right here where I'm sitting, I have like a meter between my Wi-Fi station and my laptop. And in those cases, you probably get that SNR that you need. But then you also, as you were mentioning, there's hardware effects that might be the ones that are destroying for you in those cases. So it's sort of having 35 dB SNR in a Wi-Fi, you probably have had that for a long time in certain scenarios. The reason that you haven't added this feature until now is that you need to be able to build radio equipment that are stable enough so the hardware effects are not the ones limiting you.
I see. Yeah, sure. Okay. So, I mean, in a way, it sounds to me like this terabit per second is a bit of something that be nice if you could advertise, right? It's like you buy a car and it's advertised the car can make 200 kilometers an hour. Well, it might if you're on the autobahn empty at night, but there are hardly any other roads where you could ever go that fast, of course. And so, what are, I mean, to be more specific on the practical challenges here in reaching up to this terabit? Would you like to talk a little bit more about that in detail?
Yes, I think we can sort of divide it up into three pieces. One is sort of in the physical world, the propagation environment, what limitation it has. A second thing is sort of what the analog hardware could limit us for. And the third thing could be in the digital hardware. Which one should we take first?
Oh, let's talk about physics and propagation.
Yeah. So as I was mentioning, these propagation or these bands that was identified, they are selected so that you don't have a lot of absorption by atmospheric gases, for example. There's also things like rain attenuation that becomes an issue, particularly in certain bands, but essentially in all of these bands, that if it's raining, the raindrops are absorbing the signals, for example. Then this might be also coupled to sort of the hardware, but mobility becomes more complicated because you typically need to relearn the channel every time you move a quarter of the wavelength in order to be able to rotate your constellation diagrams and things like that. And that happens much more quickly as well. And then, just the sheer thing of having more bandwidth means that if you use the same transmit powers before, you need to spread it out over more bandwidth. And then you get a weaker signal per hertz, and you need to compensate for that by, for example, using more directive transmissions or short ranges.
Right. So it sounds to me, I mean, you mentioned atmospheric conditions and rain. I mean, this is obviously only relevant outdoors, right? I mean, that's where it rains. And I'd also suppose that if there are some specific frequencies that where absorption is very high, then those could just be ignored. I mean, because we have anyways a large bandwidth. But the other thing you said here, I mean, mobility obviously will be a major issue, right? Because the Doppler scales with carrier frequency and also the range because of the reduced effective area of the antennas when you go up in carrier. So do we have a feeling for, I mean, what ranges are we talking about here with reasonable equipment?
So we can talk about two different cases, I think. So I was mentioning this like SHOSC scenario where you're going to download something over a very short distance, like 5 meters or so. There you will probably have good SNR cases. And if you have a large array, one of the limiting factors is that even if you have a large array, you need a propagation environment to be able to send multiple streams that can be separated. But if you are at short distances, there are effects that makes it possible for you to, in sort of line of sight scenarios, send different beams to different pieces of the array. Usually when you are far away, sort of if you beamform towards the receiver, the whole array sees the signal approximately the same way, so you cannot send multiple layers. But over short distances like 5 meters, that might be possible. And then you don't have rain issues of short ranges.
Yeah, sure, of course. So you're saying really, I mean, short ranges, right, like a meter or a couple of meters, and scattering in the environment so that the equipment can really, or the environment can really support multiple streams.
But over those short distances, you might be able to use. So you get first of all, with polarization, you always have a rank 2, so you can send 2 layers. But then over short distances, even in line of sight scenarios, you could use multiple layers. It's sort of this kind of geometric near field types of effects that are appearing.
Yeah, sure. Given that the array aperture is large enough, then you could support multiple streams even in line of sight. Obviously, that's a good point. Right.
But if we take the second case there with the sort of fixed wireless scenario, I've read people who think that you could deliver this over up to, say, 2 kilometers. Then it will be sort of sensitive to rain, and you will you put up a transmitter and receiver at fixed location, you have very directive antennas pointing between them, and then if you should then be able to send more than 2 layers, you need a propagation environment that not only gives you the direct link, but also some strong reflectors, and that might be a challenge to actually achieve in all kinds of scenarios.
Right, interesting. So what other limiting factors? I mean, you mentioned electronics, right? Both analog and digital. You want to say something on start with the analog. We got here the power amplifiers, I suppose, be a particular bottleneck possibly, and their efficiency.
So already for millimeter wave bands, people are talking about how complicated it is to build a good power amplifier that is efficient enough. I mean, all power amplifiers are rather inefficient, but as you go up in frequency and have more bandwidth, it might be even more so. And if you want it to be a linear amplification, you also need to operate it far from its peak efficiency. So you will need to live with nonlinearities from that case. And then you mentioned phase noise, sort of the signal generator who's creating the sinusoid of the right frequency is not perfect, so it creates distortion of the signals. And there are other things like, you need to sample now your signal with an analog to digital converter, or the digital to analog converters with a high enough resolution so you produce a signal that is in the analog domain that looks like what it should have been according to theory.
Yeah, so non-linearities and that lots of challenges here. I mean, it sounds like right for electronics design.
And also sort of theoretical things like what waveforms should be utilized. Is there waveforms that are more helpful in terms of sort of being able to use simpler hardware components. And this is something that we often come back to when there's a new generation coming up. Should we use a different waveform or not? And so far we have sort of been using OFDM for a long time and have seen that the other options of waveform is not providing much of a benefit, but it's something that comes up now in the discussion for 6G again.
Right, I can imagine. I mean, because peak to average has always been a problem, right? And OFDM, of course, from that perspective, is horrible. Perhaps we'll see a revival of constant envelope sort of waveforms then for these applications. So that'll be interesting to see.
Yeah, I remember you had some work around that in the past, where it seemed like one of the challenges is to sort of deliver not only peak to average ratio that is constant in the digital domain, but also keep it in the analog waveform.
Oh yeah, of course. Constant envelope means constant envelope on the analog signal, right? How about the digital processing?
Yes. So here I sort of wonder what is possible to do with the hardware or not. Say that we are now going to deliver data at 10 to 100 times faster than we do right now, and then we need to be able to have the hardware that can process the signal quickly enough. And I mean, one thing is that if you have say you have 50 gigahertz of spectrum, then you need to sample the signal at least 50 times at least 50 gigahertz. Probably you would like to have some oversampling, and then we look at what are the processes that we're using today. Well, for a long time we have been using processes that are operating at a 3, 4, 5, maybe up to 10 gigahertz, and then you have, instead of trying to push that rate of operation, you are trying to have multiple cores instead. And if we now go beyond those numbers there, it might be more complicated to build hardware that can handle the sheer amount of samples that need to be processed.
Yeah, of course. And even I can imagine, I mean, the digital baseband processing, even, I mean, if you have a terabit per second and you want to do like channel coding in real time, isn't that at some point going to be very expensive in terms of silicon area and power consumption?
Yeah, I think that is one of the concerns, that, of course, there is a lot of improvements going on in terms of shrinking the sizes of the transistors and being able to use the surface area more efficiently. But then people also talking about that Moore's law is dying, so we might not be able to expect that we can push up those things in the same pace as we are hoping to transmit more data. So maybe in terms of channel code, we need to go back and think about what are the most efficient channel codes that are there. And I remember reading some point that, for example, in this NASA, I'm not sure if it's the Voyager that they're sending out in outer space, that are using convolutional codes because they are very energy efficient. Potentially is sort of things that can be implemented very easily in silicon that would be utilized.
Yeah, so you're suggesting that we might be willing to sacrifice a few or a handful or so, perhaps, dB power efficient or efficiency in the COM theoretic sense. I mean, we're increasing the gap to the Shannon capacity by a handful of dB in order to gain on computational power efficiency in the actual electronics. That's an interesting prospect, which at the surface might seem like we would go backwards, right? Because coding theory has been in the last decades all about approaching the Shannon limit. Well, not entirely without constraints and computational complexity, obviously, but implementations of the coding part has never really been a dominant factor in the energy consumption. If you look, for example, at the modern, smartphone and the actual transceiver part, the digital processing, the transceiver part, just amounts for a small part of the overall power consumption. I mean, compared to the display and other components in there, is almost negligible. So that'd be an interesting shift.
Yeah, so this is a trade-off that is sort of being discussed now. Then whether it is a practical issue 10 years from now or not, it will be interesting to see. And there is a possibility that this will be a bit like what we talked about previously with analog and digital beamforming type of things, that we need to take a step backward in order to move forward with the technology, and then eventually the best technologies will come along, the hardware will be ready. But people like to push the limits faster than sometimes some of the technology components are ready.
Right. Wow, that's interesting. I mean, it really sounds like striving for this terabit per second goal opens entirely new needs and avenues for research and development. I mean, we talked a lot about going to higher frequencies, right, in order to find the bandwidth. Would it be possible, I mean, theoretically or hypothetically, would it be possible to get a terabit per second in sub-6 gigahertz frequency bands?
I think theoretically you could do that if you having the right propagation environment and the right hardware. So, I mean, to give some kind of example, a few weeks ago, Sweden had its auction for 5G spectrum in the 3 gigahertz bands, and they were auctioning out, say, 400 megahertz of spectrum there. So, if we would have 400 megahertz of spectrum and we would like to reach 1 terabit per second, I think we need like 2,500 bits per second in hertz in spectral efficiency.
Wow.
So if you say that we have like 250 users, they need to have 10 bit per second in hertz per user. So that's like 2 streams with 5 bit each. So per user, that's definitely achievable, but you will need to have like hundreds of users.
Right. So what you're saying here is that, sure, this is actually well possible, but it would have to rely on multiplexing to lots of users at the same time, so that this terabit per second is not the peak rate to one user, but the sum rate to something like, you said, 250 users simultaneously, which I suppose in turn would also require the use of a fairly large antenna array at the transmitter, right?
Yeah, so I think we are often talking about that you should have maybe 4 times more antennas or 5 times more antennas at the base station than the number of users you would like to multiplex. So you might need an array of 1,000 antennas or so, and then you need to spread them out well enough so you could be able to send narrow enough beams so that you can separate the users. I think we had sort of a crazy use case once where we were thinking about the Central Park in New York City, where you have users spread out over the park, and then you put up antennas on some of the buildings around, and they are together beamforming down there into narrow small regions around the users, and then you can have hundreds of users and reach these numbers there.
Right. I'm not so sure that use case is so crazy, actually. I think it's entirely, as far as I can understand, realistic indeed. And 1,000 antennas is not that much, right? That'd be an array of 30 by 30. And as you said, you probably want to spread them out to decorrelate the fading. And so again, I mean here, a terabit per second, some rate or some, let's say some rate, is that the word? At lower frequencies, that would require spatial multiplexing to something like maybe 200, 300 users, which in turn would entail the use of an antenna array with about 1,000 elements. So there's nothing, I think, in known physics or information theory or anywhere else that would tell us this is not possible. I think it's entirely possible, and perhaps we'll even see it happening, in a few years or decades at least.
Yeah, so I think this is sort of maybe the real use case of this technology. You have a base station at millimeter wave or below 6 gigahertz that is able to spread out 1 terabit per second among a multitude of users. And then to that base station, you need to have a backhaul link. And that could either be one of the Ethernet type of technologies or fiber technologies that can deliver that, or it could be one of these very directive 1 terabit per second links that we were describing.
Sure, right. I mean, but there is a distinction here, I think, that's worth reiterating, right? Namely that a terabit per second peak rate to a single user or a single terminal, on one hand, which is we talked about with these high carrier frequencies at hundreds of gigahertz and huge bandwidths and all that, on one hand, and on the other hand, a terabit per second aggregate or sum data rate in a cell, which is provided at any given point in time, but split among hundreds of users, which in turn, I mean, and the latter scenario doesn't require necessarily large bandwidths and could be accomplished even at sub 6 gigahertz spectrum. So that's an interesting point.
Yeah.
So when do we see or expect to see this happen in reality? I mean, the terabit per second scenario.
So one can only sort of guess around those type of things, but I think a general thing that if one look at curves on like wired and wireless technologies in terms of their capacities or peak rates, is sort of that the wired technology is often like 10 years ahead of the wireless technologies for delivering a particular rate in point-to-point scenarios. And now there is the effort of Terabit Ethernet that is going on in the wired societies, and they're hoping that within 3 to 5 years from now that should be available. Now there might be up at say 400 gigabit per second, and if we then add 10 years to that, well then maybe 13 to 15 years from now we will be able to have this type of links in some years into 6G technology.
Yeah, that's amazing. So like 10, 15 years you said. Yeah, wow. All right. I think we are probably closing up here very soon. But I was just thinking, I mean, your paper here is on scoring the terabit per second goal, right? Broadband connectivity in 6G. And 6G, of course, I suppose, is a lot more than terabits. So what else is it that 6G will contain or require or entail?
Yes, so this is sort of an extension of a white paper that I wrote together with a large number of people last year, and it's that to some extent 6G is now like brainstorming of everything that might be useful in the future, and people try to figure out what it should be useful for, and also motivate why their research is important in the future. But one thing that you touched upon was, of course, to bring up not only the peak rate, but the more user experience rate, I call by to you, what you can deliver to, say, most of the users, even at the cell edge. There are only a few users that are not getting those rates. And then I think that even if this conversation was about like peak rates to one transmission over one link, probably it's sort of the massive access that is the interesting thing, where we're going to have a large number of IoT devices, and it's often like even when you as a user thinks that you're using the internet continuously, you might be at the application layer scrolling your Facebook page continuously, but then it downloads it in small pieces. So the number of users that are there's a huge number of users, but they are active intermittently, and as you add more and more users to it, we need to have a good way of dealing with large number of users that are just transmitting a little bit of data.
So massive access, really huge numbers of devices that perhaps sleep most of the time, but then wake up occasionally and send a short packet. And of course, expect an immediate response, right? And expect high reliability in their connection as well. Yeah, so that's great. I think these are topics that we might want to return to at some future point in time in the podcast. So I think we might want to perhaps close up here for today. So this has been great fun as always, and I learned a lot as always. And thank you, Emil, and thanks to the audience. And don't forget to like and subscribe us on YouTube. And see you next time. Bye bye.
Thank you.